Today's lecture is actually on complex roots, but in order to do so, we're going to have to back up a little bit and review some other things from freshman year to be able to get there. Let's talk about radicals first and how we simplify those. So if I have a radical expression, we have to make sure it's in its simplest form. And in order for it to be in its simplest form, no radicands can have perfect square factors other than 1 inside them, and no radicands can contain fractions or have denominators that are in a radical, and no radicands can appear in the denominator of the fraction as such here. Properties of square roots is I can take any product and split it into 2 factors, and take any quotient and split it into 2 terms. So let's simplify a couple of these. If I want to simplify the square root of 24, we remember simply that we find a perfect square within here. So 4 is 1, and then times 6. You never want to use 2 because 2 is not a perfect square. The square root of 4 is 2 root 6, and that's done. 135, if I want to find a perfect square in there, I can just start guessing away. Even though I know 5 goes in, 5 is not a perfect square. The only perfect square with 5 in it is 25 that I can think of, and I know 25 doesn't go in. So I'm going to try 9, and it turns out that 9 and 15 is 135. So square root of 9 is 3 root 15, and that's simplified. Now if I want to multiply radical expressions, I take those 2 products, multiply them together, and I get a new term. If I have coefficients out in front, I can multiply the coefficients by each other and then multiply the radicands by each other and get their product underneath. So in this case, I can multiply 5 and 10 because they're both radicals, get root 50, but that's not simplified because I know that breaks down into 25 and 2. So I have 5 root 2. And then here I have 2 and 3, which is a product of 6. And now what I'm going to choose to do is the following. I don't want to go 32 times 45. I'm going to take and break down 32 into 16 and 2. Then I'm going to break down 45 into 9 and 5. And notice from here I can pull a 4 from the 16. I can pull a 3 from the 9. And they have root 2 and root 5 left. So therefore I can multiply these guys together, get 72 root 10, and be done. So in this case I have radicals with a denominator, and we're not allowed to have that. So we must rationalize. If you remember rationalizing, we multiply the radical by some form of 1 to remove the radical from the denominator. So in this case that's root 7 over root 7, and multiply top times top, bottom times bottom. That gives me root 21 over root 49, but luckily root 49 is an integer of 7. So now we've gotten rid of the radical in the denominator by rationalizing by a form of 1. In this case, what I like to do is I like to break down these denominators first, if at all possible. So I see I have 13y in a radical. 20 breaks down into 4 and 5. And I know that the square root of 4 is 2. So now all I really have to do is get rid of the root 5. So I rationalize by root 5 over root 5. Gets me a total of 65y in the numerator, and then root 5 times root 5 is 5 times 2 is 10, and then I'm done. Finally, adding and subtracting. You can only add and subtract to like roots, and it's just like terms. You keep the same root just like you would keep the same variable and add the coefficients out in front. So in this case I have like roots of root 3. 9 minus 4 is 5 root 3. In this case, I have an unwritten 1 right out in front of the radical here, so this is 1 minus 7, which is negative 6 root m. And I could only do that because I had like roots. Now in this case I don't have like roots, but I can simplify each of these. So I have root 9, root 5, and root 4 and root 5. So this goes to 3 root 5 minus 2 root 5, which is 1 root 5, or root 5. There's an implied 1 out in front. Likewise, I can do the same here. This is 9, and then that's 25 and 3 and 2, and that's 25 and 2. Notice this goes to 45 root 3. This goes to 10 root 2. But now I'm stuck because I have no more like roots. So that's just my final solution. When we have multiplications and additions together, we can distribute. Notice here I have 10 root 15 and 6 root 18, but my 18 breaks down, so I'm going to have to simplify that to root 6, root 9, and root 2. That's 10 root 15, and this is 3 times 6, which is 18 root 2. Here I'll have to FOIL, and again I can't add these two because I don't have like roots. So I FOIL and I get 6 root 10 plus 2 root 50 plus 9 root 2 plus 3 root 10. I'm going to simplify the 50 and add these two since they're like roots, so that's 9 root 10 plus 2 root 25 root 2 plus 9 root 2. This gets me 9 root 10 plus 5 times 2 is 10 root 2 plus 9 root 2. The root 2's can combine, so that's 9 root 10 plus 19 root 2. Alright, and let's do one more review. So in this case, notice we have a radical on the bottom, and we can't have radicals in the denominator, so what we have to do is we have to rationalize again. And if you remember from freshman year, we have to rationalize by something called the conjugate. Conjugate is the same expression as the denominator, but with the opposite sign in the middle, separating the two terms. So my conjugate in this case is the same first term, 2 minus root 3, by that definition below. And I have to multiply by a form of 1 so I don't change the value. This is 10, I'm distributing, minus 5 root 3. I FOIL the bottom, which goes to 4 minus 2 root 3 plus 2 root 3 minus root 9. The 2 root 3's go. This leaves me with 10 minus 5 root 3 over, this is 4 minus 3, which is 1. So this is 10 minus 5 root 3, and now I have no more radicals in my denominator. So all of this to get to today's lecture, which is the complex number system. Now, at some point, mathematicians came up with an issue. They had a problem to solve where they had to find out, well, x squared times what is equal, or solve this. X squared equals negative 25. What multiplied by itself is a negative number? They couldn't do it, so they got a little frustrated and decided to make up a new number system. They said, okay, well, here's what we're going to do. We're going to let this thing I be equal to the square root of negative 1. And this is going to solve our problems. We're going to make this by definition, which means nobody could question it. And then by definition, they said, and we're going to let I squared equal negative 1. Therefore, I cubed would equal negative I, because I times I squared is I cubed, and negative 1 times I is the same thing as saying I cubed. I to the fourth then is I squared times I squared, which is negative 1 times negative 1, which is positive 1. if we wanted to find I to the 34th or 35th, I think the easiest way is to put this in terms of I squareds. So this is I squared to the 17th power times I. I squared is negative 1 to the 17th power times I. Negative 1 to the 17th is negative 1 times I is negative 1I. I to the 61st is equal to I squared to the 30th, which is I to the 60th, times I to the 1st. I squared is negative 1 to the 30th times I. Negative 1 to the 30th is 1I. So what is a complex number? Complex number is made up of a real part, which is the first part of the term, and an imaginary part, which is grouped with the I. In order to add these things, pretty simple. It's just like terms. Add the real with the real, imaginary with the imaginary. So this is equal to 1 minus I, because there's 4 minus 3, and there's negative 5 plus 4. Likewise, I could distribute my negative 1 and have 5 plus 8I plus 3 minus I. Combine like terms, there's 8 plus 7I. When I'm multiplying, just FOIL right away. So in this case, I have negative 6, negative 4I, plus 12I, plus 8I squared. Now the only thing we have to do here is clean up a little bit. That's negative 6 plus 8I, adding your like terms again. I squared we know is negative 1, so negative 1 times 8 is negative 8. Clean this part up, that's negative 14 plus 8I. In this case, we have i's in denominators, which means there's really a square root, because this is the square root of negative 1. Therefore, in this case, what we have to do is we have to simplify this by saying, all right, if I take and rationalize by I over I get 4I on top, which is okay because there's a square root of negative 1 on top. But this is 3I squared. I squared is negative 1, so that's 4I over negative 3. In this case, rationalize again by I over I. I don't need to worry about the 6 because that's positive. I have to distribute on top now, so this is 4I plus 5I squared over 6, it's a squared, over 6I squared. Thus gives me 4I minus 5 over negative 6. Typically, they won't leave a negative in the denominator. They'll bring that up to the numerator. So if I multiply a negative by my numerator, like so, they'll leave the answer as 5 minus 4I over 6. So here we go again with the fraction. We have an I in the denominator, which is the square root of negative 1. But we've got two terms, so we've got to use a conjugate again. Conjugate's the same first term, that's 2. Opposite second term, minus 5I. Multiplied by a form of 1. I'm going to have to FOIL both of these, so on top I have 2 minus 5I minus 8I plus 20I squared over 4 minus 10I plus 10I minus 25I squared. I end up with 2 minus 13I minus 20 because I squared is negative 1 over 4 plus 25 because negative 25 times negative 1 is positive 25. Cleaning this up gives me a negative 17 minus 13I over 29, and there we have it. Finally, let's talk about simplifying a negative radical. Well, we can't really simplify a negative radical, so anytime you see that negative radical, take and make that equivalent to I, because that deals with the square root of negative and root 72. Therefore, we can now play with 72 just like we did prior in the beginning of today's lesson. I have I root 36 root 2, which gives me 6I root 2. And that's all we've got. Make sure you do your summary and your connect ed. We'll see you tomorrow.